I want to tell you today about when the universe was very young. In the scale of the universe, young means 300,000 years old. Today the universe is about 13 billion years old. And so if you think about the ratio of those two numbers, the universe at age 300,000 years compared to today is about the same ratio as a day-old baby to a 100-year-old person. So it's literally when the universe was a new baby. The universe started out much hotter and much denser than it is today. And in fact, the universe, if you go back far enough, the universe is arbitrarily hot. When the universe was in its infancy, at its one-day-old state, it was 300,000 years old, it had a temperature that was light in every direction, just a hot soup of light and charged particles. You had charged particles in the universe because the light was so intense that the charged particles could not come together and make neutral atoms. If a neutral atom would happen to form, some radiation would come along and knock it apart again. So you have a soup of stuff that's called a plasma. The early universe was plasma. Now, how do we know this? Well, we know it because the universe is not a static place. The universe is changing. And in particular, the main thing that the universe does is it expands into neutral atoms again. So then the universe fundamentally changed. Before this time, the radiation would move around, and it wouldn't go very far before it got to a charged particle. And what radiation does when it gets to a charged particle is it bounces off of it. So the radiation would go around and it would bounce off this charged particle, and then it would bounce off another charged particle. And any bit of radiation would not go very far before it would move off in a different direction. Now, if you think about what the universe would look like at that point, if you were back early in time and you were standing there watching things, any of the radiation coming into your eyes would not have traveled a very large distance. So it would be like being in a fog, ways in front of you, because the radiation is bouncing off of the fog particles into your eyes, and you just see a very small region around you. That's what the universe was like. It was literally a fog of light. It cooled off, and at some point, the radiation lost enough energy that it was not able to break apart neutral atoms anymore. So when the charged particles came together to form neutral atoms, the average radiation coming, so the radiation which before was bouncing around, now suddenly had nothing to bounce off of anymore. Now this radiation, which had been bouncing back and forth, can travel freely for the entire rest of the history of the universe. So if you have some photon, it last scattered sometime around 300,000 years into the history of the universe. And then it may very well have traveled from that point until today, never having interacted with matter in the entire rest of the history of the universe. It's because we can see this radiation from the early universe today. Now, in the early universe, the last time this radiation scattered, I told you that the universe looked like the surface of the sun. But you know very well that when we look up at the sky does not look like the surface of the sun. And that is only because of a very simple
of the radiation in the entire universe today is in the form of these microwaves, which have been propagating freely for 13.7 billion years. We can see these microwaves with specially designed telescopes by country. If you build the right kind of telescope, you can see radiation, which is coming from when the universe was in its infancy. We see signals from the early universe. It's as if we literally have a baby picture of the universe. That means we can figure out things about the universe from looking at this radiation. Radiation was first discovered essentially by accident in 1965. And we didn't know it when I first started working on this in the early 1990s. But today, by looking at this radiation, we have figured out actually quite incredible. If I look at some direction of the sky, I see this radiation coming from very far away. It's traveled the whole distance of the universe. See what the radiation of the universe is like over there. I can look in this direction and see what the universe is like over there. It turns out that if you look at this microwave radiation, it is almost the same in every direction. It's very, very this plasma that was almost the same everywhere. But it wasn't quite the same everywhere. And you actually know this from a simple thought experiment. Imagine that the universe was absolutely the same in every direction, in every place at early times. Well, what would differentiate any place from any other place today? We know that the universe is not the same in all places today, because otherwise we wouldn't be here. We have it down to the ground, we have it up to the sky, and those directions. Galaxies are things to be called little island universes. We know that galaxies are spread throughout space. In between galaxies is almost unfathomable emptiness. So we happen to live in a very special place in the universe. If the universe was perfectly uniform at early times, there would be no special place. So you may know that as I talk to you, there is sound coming out of my mouth. Actually, what my mouth is doing is creating variations in air pressure by my vocal cords moving back and forth. Those variations in air pressure move out through the air, getting to your ears, press your eardrum back and forth, and that's what we call sound waves. They are propagating small differences in pressure in the air in this room. Something similar happened in the early universe. There were sound waves that moved through the universe. The universe was filled with this fog of radiation and charged particles, and sound waves could move through that just as sound is moving through the air in this room today. When we look at the sky and see the radiation in that direction being a little bit different from the radiation in this direction, most of that difference is due to sound waves propagating through the early universe. Now, I find this, as a scientist and as a musician, to be quite phenomenal. We can actually see the sounds of the early universe. We have these sound waves propagating through the early universe. That means at the moment that all the atoms became neutral and all of the radiation started flowing, well, over here it might have been a little bit denser because the sound wave was more dense in that place. Over here it was a little bit less dense because the sound wave had spread apart the plasma in that place by a little bit. And we can see those differences today in the radiation that we get from the sky. Now, this would only be a scientific and musical curiosity. if not for the fact that the universe was very simple in the early days. And these sound waves are a reflection of the simplicity of the universe. We can measure the properties of these sound waves to great precision. At least we can do that now. This has been a heroic effort by experimental physicists over 50 years. When the microwave background was first discovered, we had the capability of saying that over there and over there, the intensity of this radiation is the same to within about 10%. And now we can make maps of the sky where we map out the pattern of hot and cold spots to a precision of a part in 10 million. So we have improved by a factor of 1 million in 50 years. These improving measurements have given us an extremely high precision measurement of the properties of the sound waves in the Earth universe. And quite fascinatingly, the properties of these sound waves depend very sensitively on the nature of the universe as a whole. If the universe has a little bit more stuff in it, it has a little bit more electrons and protons in it at early times, that will enhance the sound waves compared if it has less. If the universe has more dark matter in it, dark matter creates the gravity which drives these sound waves in the first place. If you increase the amount of dark matter, you will change the properties of these sound waves. If you change the overall geometry of the universe, then as the light from these sound waves travels from early times to late times, the path of the light will be altered, and the pattern of hot and cold spots we see in the sky will change. So by starting with the properties of these sound waves, we can work out what the nature of the universe is. It turns out that the universe is a very simple place. One of the things we have learned from these sound waves is that we can make a model of the universe that describes everything that happened from early times until today, 13.7 billion years of the history of the universe, with the physics that we know about, plus 6 numbers. We can write down 6 numbers which encapsulate our entire model of the universe. I mean, that's quite amazing. You can't characterize your part full of growth. Now, that doesn't mean that all of us cosmologists are out of a job, because it turns out that while the universe is simple, it also contains some enduring mysteries. One of those 6 numbers tells us that the universe must have dark matter in it. There's a lot of dark matter in the universe. In fact, there's 6 times more dark matter than ordinary matter in the universe. And all we know about the dark matter is that it's not made out of protons and neutrons and electrons like we are. Another thing we found out is that the universe has some other, and yet it's the thing that dominates the dynamics of the universe today. It makes the expansion of the universe speed up, and we don't know why. These 2 mysteries are going to keep people like me employed for a lot of years, and keep those grants coming in, and keep these artistic performances happening. A third thing that we don't understand is where did these small perturbations that lead to the sound waves come from in the first place? We suspect that these might be evidence of something that happened not when the universe was 300,000 years old, or even when the universe was 3 minutes or 3 seconds old, but maybe when it was 3 trillionths of a trillionth of a trillionth of a second. So these sound waves in the early universe perhaps contain the key to understanding the way the world is at an incredibly early time and at energies that are vastly higher than we can ever probe in our terrestrial laboratories. In the late 1500s, the astronomer named Johannes Kepler figured out the pattern of planetary orbits around the sun. He laid these down in a book which was called Harmonia Mundi. That's Latin for the music of the world. Kepler, in addition to being a brilliant scientist, was also a mystic and a musician. And Kepler thought that the orbit of each planet was associated with a musical motif. That literally, as planets moved through space, they created music. And we now know that Kepler was right in some sense metaphorically, but almost literally. It's not the planets that make music, but it's actually the early universe itself. The entire universe was musical in its early moments. So, Harmonia Mundi indeed.